Hello, I'm Mr. Klingler. Today we're going to talk about circular motion with diagonal forces. The best way to attack this is to just start with a problem. So, a car travels around a frictionless curve of radius r and banked at theta degrees above the horizontal. At what speed can the car successfully navigate the curve? The first thing we should consider is why we have frictionless and banked. Well, imagine a horizontal curve. You would have the center of the circle. You would have the car, and it would need to go in a circular path. Well, if it was frictionless, the problem is nothing is supplying the centripetal force towards the center. If it's frictionless, the free body diagram would simply look like this. Therefore, we're going to need something as a centripetal force. But what? The key is the banking. So let's start solving this problem and see how the banking plays out. The first thing I need to do is draw a free body diagram. I realize I'm trying to find the speed of the car. So this is my diagram. Let's put the forces on it. Well, what forces are acting if it's frictionless? Clearly, we have weight pointing straight down. We also have surface, so there must be a normal. Now we know why it's banked. Because normal is going to help provide the centripetal force towards the center. Notice that I've drawn a side view of the diagram. I've indicated where the center of my circle is going to be, and often I draw this circle just so I know what's going on. Okay, so that's my circle. I seem to be in pretty good shape. One quick question though. Which of these two forces is going to be bigger? Well, if I think about it, the net force needs to point towards the center of my circle. So the net force needs to point this way. If that's true, that must mean that the forces in the y balance out. Okay, that means there's a little bit left over force in the x. Therefore, I suspect that Fn is going to be greater than Fw. Thinking about the components, I have a little bit of normal force balancing the weight, and the remaining normal force is pointing towards the center of my circle. Great. Notice, because I've oriented it this way, I should be careful about what I choose for my axes. Whenever you write a sum of the forces equation in a circular motion problem, you want to make sure one of the axes points towards the center of the circle. Well, it seems clear that I'm going to want to use traditional xy axes in order to have my net force point towards the center of my horizontal circle. I would also note that on inclines we often think about doing parallel and perpendicular. You would almost never do that in a circular motion case. Alright, let's continue. Well, I have my free body diagram. Now I should probably write a free body equation. So, I'm going to start with some of the forces in the x direction because, well, my center of the circle is in the x direction. So, it looks like I have Fn, but not all of Fn. Only Fn in the x direction. Okay? Continuing to solve this, that would be Fn, and now is it sine or cosine? Okay, well, let's do some trig. If that's theta, I know that's theta, which means this angle right there is theta. Therefore, it looks like I'm going to be using opposite. Looks like I'll be using sine theta. What are my total forces equal to? Well, this is the forces acting centripetally, so my total forces must be equal to mv squared over r. I'm stuck. It would be really helpful to know Fn. Well, let's find it. You remember the problem. I'm going to erase it. So, some of the forces in the x. Now we'll look at some of the forces in the y. Looking at some of the forces in the y, there are clearly two forces. The forces in the y are in equilibrium because my net force is pointing towards the center of my horizontal circle. Looking at theta, the y part of this is going to be cosine. Okay, I can solve for Fn. I'll now take this and plug it back into here. I'm a little concerned that I don't know mass, but maybe something special will happen. And indeed it does. I have mass on both sides. I can cancel those out. Now I'm only left with variables. So I can solve for v. I'm going to end up with the square root. I bring my r over. Sine divided by cosine is tangent. This is my solution to the problem.
This is not a note card equation. If you were ever to solve a problem similar to this, you would need to go through the steps that Mr. Klingler just introduced to you.
Now, one more thing to consider before we go. What would have happened if there was friction? How would this have changed the problem? That's a good question. Well, I have to redraw my free-body diagram. But what direction would friction point? Well, this suggests, without friction, that there's only one speed at which I can successfully navigate this curve. Any faster than this, and I would travel out of the curve. Any slower than this, and I would start to slide in. So friction would help fight that tendency. If I were going too fast, friction would point, well, I try to slide this way, friction would point down the incline. If I was going too slow, friction would point up the incline. Let's just draw the free body diagram and see what that looks like. There's my car. I would have, well, let's pretend we're going too fast. Force of weight, force of normal, and force of friction. Now the question is, how many of those forces are acting centripetally? It should be clear that our circle is still in the horizontal direction. We still need a net force towards the center of our circle. Therefore, it looks to me like we'd have Fn and force of friction, or parts of them, pointing me or away from me in the radial direction. My sum of the forces equation then would be Fnx minus force of friction in the x. Clearly I need to do some trig in order to finish solving this, but this would get me a good start towards the solution of the problem. Of course, my sum of the forces in the y would also be slightly more complicated. I hope this was helpful. Thank you.